let us begin with a recap, and this is going to be a rather big and long recap because we did quite a few new things in the previous week. So, the main thing we are looking at right now is LDPC codes. Okay. So, we saw that these are defined by sparse parity check matrices. Okay. So, as we go along in this recap, I am going to ask you a lot of why questions just to think back and see that we know the reasons for why these things are true. So, why do you think this sparse plays a role? Why is sparsity important? Yeah. So, in your decoder, if the parity check matrix is sparse, in your decoder the extrinsic information is very likely to be independent. Okay. So, that is the idea, that is the reason for sparse, and also the quality of the extrinsic information will be high when you have sparse parity checks. Okay. So, those are ideas behind why the parity check matrix has to be sparse. So, after this you classify. So, the classification is based on degree distribution. Okay. So, that is an important method in understanding LDPC codes. The degree distribution plays an important role here. Okay. So, there are two different types of degree distributions. One is node based, okay, with respect to nodes, and the other is edge based degree distribution. Okay, and they both have some relationships between each other, as you can imagine, right. So, given the node based distribution, which we called as L of x R of x, you can uniquely compute the edge based distribution lambda of x rho of x. Okay. So, this is a good exercise, I will urge you to do it. Okay. So, given an arbitrary node based distribution L of x R of x, how will you convert it into an edge based distribution lambda of x rho of x. Okay. So, there is an explicit formula for it. It's an interesting assignment also, it is not too difficult, it can be done without too much trouble. Think about how you might want to do it. Okay. So, once again the crucial fact to remember here is the degree distribution along with the block length n specifies in fact an ensemble of LDPC codes, it does not specify a unique parity check matrix. Okay. So, in a way it is really surprising if you were educated a lot in classical codes and Reed-Solomon codes and groups and fields and all these things, and suddenly somebody says, you know what, here is a code that has amazing performance, and how do you construct the parity check matrix? Put the ones wherever you want. Okay. Just make sure that the number of ones you put follows some rule, that is it, right. So, it is a bit counterintuitive and very surprising that some code that you build like that without even bothering about various structures that or things that you are doing, you just put it wherever you want and it can perform very well. Okay. So, that is the idea behind these kind of systems. So, it's in a way, if you think about it, you are going to a large enough block length so that any code is likely to be good. So, it does not matter that you have to really optimize the structure of a parity check matrix, that is not so important. Any code is likely to be good when you go to a large enough block length, that is something that is known to many people, okay, known before. Okay. The only problem is with any code you can't decode, you know. So, you put your ones in such a way sparse and following some rules so that the decoding is going to work. So, that is the key idea here. Okay. So, that is the way you have to think about that. Okay. And what? So, the main thing that the degree distribution controls is the density evolution. Okay. So, if you think of decoding, so decoders are important. So, decoding is done by, how is the decoding done? By message passing on Tanner graphs. Okay. So, the Tanner graph is an important notion, and you do message passing on Tanner graphs, and the performance is controlled by a threshold phenomenon is observed in the phenomenon is observed in the decoder, and that is determined using density evolution. Okay. And indirectly or directly, in fact, the degree distribution controls the density evolution. Okay. So, you get a threshold for the degree distribution, all right. So the way you would go about working with LDPC codes is, once you have a particular channel, say a binary symmetric channel or AWGN channel, and you have some modulation scheme defined, first thing you do is you try and optimize your degree distribution to get the best possible threshold for a given rate. Okay. So that is a complex optimization. It will take a lot of effort, and it can be done out, it cannot be done online or anything like that. It is done beforehand, and you decide a degree distribution. Like I said, there are also databases available for good degree distributions. Once you have a good degree distribution, you have to follow certain construction procedures for constructing a suitable parity check matrix. Okay. So the construction procedure, I have not spoken much about it. Like I said, mostly it is random, okay, but there are also some pseudo random type constructions available. Okay. So you do that, you get a parity check matrix from the ensemble. Okay. Once you get a parity check matrix from the ensemble, you simulate and check if it is good enough or not for your purpose. Okay. So that is the method or program that you follow to work with LDPC codes, to design LDPC codes. Okay. So there are 3 or 4 main blocks that you need. One program you need for optimizing the degree distribution, another you need for constructing the parity check matrix, and another for doing encoding decoding. Okay. So all these things you should have and if you want to work with LDPC codes. Okay. Any questions on this, on the general idea, why it is working, how it is working, etc. Any comments? It is fine. Or last week was quiz week, or current week is quiz week? Yes. Yeah, so we do not really speak about minimum distance anymore. The reason is, I mean it is critical. I have to tell you that it is critical, it is important. It controls a certain region of the bit error rate curve. Okay. So usually what happens is, when you run these decoders, and when you look at, say, error rate versus SNR or some channel parameter, it will have this threshold phenomenon. Okay. Of course it will not keep on going down forever. Okay. So at some point it will start flattening out. Okay. So this part is controlled by the minimum distance. Okay. Okay. So this is called like the waterfall region or something. This is called the threshold region, threshold or waterfall region, and this is pretty much controlled by the random properties of the matrix. I mean, minimum distance does not play a big role here. Okay. There are good reasons for that also, people have analyzed it. Then you will keep on going down, and eventually the minimum distance will start to play a role. Okay. So this is called the error floor region. Okay. And minimum distance plays a role here. Okay. So minimum distance is important for this. But usually what happens is, for most LDPC codes, if you design your random construction properly, okay, when I say properly, I am not defining it very clearly, but there are papers about how to do a random construction of LDPC codes, how to make sure you don't get into trouble. If you follow all those rules carefully, it turns out this floor will not hit you in terms of FER. This floor will happen lower than at least 10 power minus 6. You can do a design where this floor will happen below 10 power minus 6. Okay. So you can do that design quite easily, and 10 power minus 6 is something you can simulate and verify. Okay. On most channels you can ensure this. Okay. So if you are looking at wireless applications or applications where 10 power minus 6 frame error rate is really an overkill, then you do not care, you just use this and you are happy. But if you want to look at storage or other applications where 10 power minus 6 is still way too high a frame error rate, okay, so you can imagine today's data centers have data in the millions of terabytes. I don't know if it's millions of terabytes, but it's a lot of lots of zeros after ones, right? So when you have that, then 10 power minus 6 is definitely not acceptable. Okay, so if you want 10 power minus 15, 10 power minus 20, there is no way you can simulate. Okay, there you have to have a minimum distance for guarantee. Okay, all right. So if you have a random construction method for LDPC codes, which also gives you a guaranteed good minimum distance, you can become very rich. Okay, so think about that. I mean, people like Google might buy from you. They run a lot of data centers. So but it's a difficult problem. I mean, people are still working on it. Maybe I am also working on it. So who knows? Somebody might find it somewhere. Okay. So it is important. So my answer is, it is important. depends on the application. If your application only wants a constant frame error rate which is low enough, say 10 power minus 4, 10 power minus 5, then you do not have to care too much about it, but you still have to pay some attention to the way you construct your matrix, so that you do not get a very bad minimum distance, like minimum distance 2 and all will really kill you. You should avoid those things. As long as you avoid very low minimum distances, even if it is slightly low, it is not a problem. Once again, you might ask me, what if I construct a parity check matrix and find the minimum distance for that code? That is a difficult problem. Like I said, nobody knows how to find minimum distance given a parity check matrix. Only in your exams I will ask you for very small problems and you have to find it, but it is for small problems. Large size problems, it is impossible to do that. Nobody knows how to do that. Okay. Alright, so now the last thing we were talking about was soft message passing decoding. Let me quickly do a recap of that and then we will proceed. Soft messaging, I do not know why I wrote that, message passing. Okay, so like all message passing algorithms, there are two steps. The first step is, let me draw the bit to check step first. Okay, in the nth iteration, I think this is V. Is this V? Okay, that's U. Okay. U1, U, I do not know, is it I? Oh, we did WC minus 1, no? Okay, so I had a superscript maybe L minus 1. This is bit node, no? This is a bit node. Bit node is WC, no? WC column and row. I know check, C also is for check, so it is a bit complicated. So VL1 and this is, so if you received, I must have used Li for this. Did I use Li for it or L, just L? Li, okay. So in the V1 L is computed as Li plus U1 L minus 1, maybe this is U2, no? Okay, U2 L minus 1 plus, oh, to WC, right? That is not minus 1 there. Thank you. All the way to UL minus 1 WC. Okay, so that's what you do for that edge, and the other edges you do something similar. Okay, so you ignore the extrinsic information that came on that edge, but you add up everything else and send it. Okay, so you have to think of the message as the log likelihood ratio for the ith bit. Okay, so every message that you are passing in soft message passing is a log likelihood ratio for the ith bit. Okay, some estimate of the log likelihood ratio based on what you know at that point. Okay, and then when you send back, you have to use the extrinsic rule and make sure that you do not send back information that you already have. Okay, so that results in something called positive feedback. You might have read about positive feedback and why it is bad. You know, if you keep on feeding back what you knew, then suddenly everything will blow up and you will go to either side, and after that you can't do anything about it. Okay, so it is not good to keep on sending back information that is known, so you have to avoid that. Okay, so this is for the messages from left to right. Okay, and for messages for right to left, okay, so it is a little bit more complicated. Okay. Okay. So, but the formula is quite straightforward. In fact, at this check node, you know that all these bit nodes have to XOR to 0. Okay, so clearly this bit node has to be equal to the XOR of all these other bit nodes. Okay, so that is the rule you use to compute the log likelihood ratio. Okay, so once you know that the log likelihood ratio is what is being sent, all you have to do is use the computation that you know already. Okay, and that computation is 2 times tan hyperbolic inverse of the product of tan hyperbolic of all the incoming LLRs, right. Okay. So that is what you send back on each edge. Okay, what will you send on the second edge? Again the same formula, except that what you will use here will be V1L, V3L, so on till VWRL. Okay, so that is the idea. Okay. So you repeat this iteration several times, and usually you conclude on the bit node side. Okay, so how do you conclude? If you want to conclude or finish your iterations at the Lth step, then you have to make a decision on some kind of final LLR. Okay, so the final LLR after L iterations okay, this is the Lth iteration. After the L iterations, the final LLR is written as Li, okay, the first Li plus, okay, now you add everything. Okay, so when you compute the final LLR, there is no extrinsic, right. So everything is, I mean, all the extrinsic information has to be added together. Now you are not trying to pass back something to anybody else. Okay, you are trying to make a final decision. So you simply add everything. Okay, so U1L plus U2L plus so on till UWCL. Okay, so this you say is your final LLR after L iterations. Okay, so how will you decide based on the LLR? That is all. If it is greater than 0, you say it is bit 0, and if it is less than 0, you say it is bit 1. That is it. Okay. Okay, so since we are back to the old laptop, I might have a file which I can show you something. Okay, so there are lots of slides here. So let me see. Let me see if I find any interesting slide. I'll stop there and talk about it. Okay, so this is soft decoding. I might have like a summary. So this is the summary that I had. I wanted to point out one thing in the soft decoder which I may not have mentioned in detail here. So the rule that I gave you for check to bit message. Okay, so have I swapped U and V here? I think in this notation. Okay, sorry for that. I think this is old presentation, but anyway, it does not matter. So if you look at the check to bit message here, it uses a function f of x, which is some log tan hyperbolic mod x by 2. Okay, so it turns out if you use this function, then you can make that operation very efficient. That is all. Okay, so you will see a lot of people using this function log tan hyperbolic mod x by 2, and I do not want you to be surprised by it, but it is not very different from doing 2 tan hyperbolic inverse. You divide by 2, take tan hyperbolic on both sides and take logarithms, you will get this formula. Okay. So in VLSI this is particularly nice because all you have to do is have a lookup table for this one function f. Okay, that is it, and everything just involves that same function f. Okay, so that is one thing I pointed out. I think I mentioned that briefly in the okay. So this is I do not know if you can see the line numbers very clearly on the left hand side. How many line program is that? 36, and you can read the first lines maybe. So EB and not DB and rate and maximum iterations and n blocks. Okay, so 100 or something. And then there is a parity check matrix H that has been constructed. I do not know if you can read it. Okay, so I am trying to read that, and then I am doing the decoding. Okay, so this is the entire soft message passing decoder for LDPC codes, for an arbitrary LDPC code with an arbitrary degree distribution written in MATLAB. Okay, this is code for that, and that's all. So that's all it takes, just 36 lines. Okay, in MATLAB. I'm sorry. It's okay. I mean everything. It's only 36 lines because MATLAB has some very smart commands to deal with sparse matrices. If you are very smart about it, you can write a 36 line MATLAB program. Okay, so it will work quite fast. Okay, so I can, even in my laptop, which is a reasonably low end machine, as in maybe not very high end, maybe has like a 2 gigahertz processor or something. Okay, so it's not very fancy. You can run a million blocks of length 1000 code or something within a few hours. Okay. So it's not very unheard of to do complicated simulations with LDPC codes. Okay. So it's easy to do that. It's a small program. I wanted to show you that because you may, after all the description, you might think it's going to take a lot to implement it. It's very easy to implement it in MATLAB at least. Okay. So this plot you might have seen. I think I've shown you this plot, and this plot really captures all that we discussed. I mean, so if you see this, the capacity for this is for 8 half codes. Okay, 3,6 regular, so 8 half codes, and then there is the threshold which will come at around some 1.1. I think it's about 1.1 dB, okay, in EB over N naught for 8 half. Okay, and then you have 3 curves here, one for length 1000, another for length 10,000, another for length 100,000, and you can see how good an estimate the threshold is for the behavior of the decoder. Okay, and I am going down. This is only bit error rate 10 power minus 4, but even if you do frame error rate, you will get very similar behavior. Okay. So this really justifies many of the assumptions we made in the density evolution simulation, in the density evolution method, right. We made a lot of assumptions, and at the end of the day this justifies all those assumptions. Okay, you might want more intuitively pleasing justifications, but simulation is ultimately the best certificate for making for the analysis. Okay, so this is that. Then okay, let me see if there is any nice slide that I want to show you on density evolution and all that. Okay, so we haven't spoken about density evolution, right. So we will come back to this when we do density evolution. Okay, so the next point is how do you do density evolution for soft message passing decoding. Okay, so previously we did density evolution for the Gallagher array decoding in a binary symmetric channel. That was hard message passing, right. What was passed was just a bit, and we could easily track the probability of whether the message is correct or wrong. Okay, so here we need some more effort, and let us try to do that. Okay, so the setting is as follows. Okay, so you have a code word. Okay, you have the all 0 code word. Okay, we will assume the all 0 code word. Once again, that can be rigorously justified. You can show that the all 0 code word is not a problem. Okay, then this goes through BPSK. When the all 0 code word goes through the BPSK modulator, what do you get? Okay, you get all plus ones, right, all 1 symbol vector. Okay, to this noise gets added. This is normal, mean 0, variance sigma squared, and you get a received vector R. Okay, so the input to the decoder is not exactly R, it is the input log likelihood ratio, right. The log likelihood ratio is what? So if R is R1 through Rn, the input to the decoder is actually the log likelihood ratio vector, which we have been calling L1 through Ln, and what is Li? Simply 2 Ri by sigma square. Okay, so if you transmit the all 1 symbol vector, okay, what will be the distribution of Ri? Ri is what? Ri is 1 plus Zi, right, and what will be the distribution of this? Normal with mean 1 and variance sigma square. Okay, and Li is 2 times Ri by sigma square. Okay, you can do a quick arithmetic and check that Li will also be normal with mean 2 by sigma square and variance 4 by sigma square. Okay, 4 by sigma square or sigma per 4? 4 by sigma square is correct. Okay, all right. So that is something you can find. Okay, so why did I want to find the distribution of Li? Okay, because Li is the first message that is passed from bit node to check nodes, right. So remember in the first iteration, what happens in the first iteration? You have a bit I and it is connected to WR check nodes, and what is passed in the very first iteration in every edge? It is simply Li, simply Li. No. Okay. So L sub I is what you are sending in the first iteration. So at least we know the distribution for the very first message accurately. Okay, given that our channel is a Gaussian channel, we know the distribution at least for the first iteration for the bit to check node message, right. Okay. Now, okay, so the question is, how do you track this as the iterations proceed? Okay. So let us look at what happens on the bit node and the check node, etc., and you will see it can be tracked without too much of a problem. Okay. So the crucial assumption is all 0 code word, which means all the LIs have the same distribution. Okay. In case if you cannot assume the all 0 code word, what will happen? You cannot assume that every edge will be identically distributed, because if it is +1, then it is going to be +2 base sigma square. If it is -1, then it is going to be minus, right. So there is a problem there with not assuming the all 0 code word. Okay. Because you are assuming the all 0 code word, you have only one distribution to track. Okay. Now what I am going to do next is to look at the bit node operation and the check node operation and assume that I know the PDF of the incoming messages, and I will further assume that all those messages are identically distributed and independent. Okay. Once I assume that, let us see how to track the PDF as it goes through the bit node and the check node. Okay. It is not too difficult, you will see the operations are quite standard and you can do it very easily. Okay. Not very easily, but at least theoretically it is very easy to describe how to do the tracking of the PDF. Okay. Once you track the PDF, that is all you have to do for density evolution, right. What is density evolution? Ultimately you are tracking the distribution of the message from iteration to iteration. Okay. In the first iteration, first step, I know what the distribution is, and if I tell you now how to track the distribution through the check node and how to track the distribution through the bit node again, then you can find the distribution for any iteration. Okay. So that part is clear. Okay. So all you need for density evolution is to figure out what happens to the distribution at the check node, what happens to the distribution at the bit node. Okay. And we will again make our standard assumption that at the check node all the information that is coming in is going to be IID, okay, independent and identically distributed. Okay. And that is justified because we are using the locally tree idea. Okay. So we know that every neighborhood is locally a tree with high probability, at least probability 1 over n. So you will not get any repetitions. So if you do up to only L iterations, you are not going to be getting repetitions anywhere. So you will have IID distributions for the messages. Okay. So the justification is again only the tree neighborhood in the local neighborhood. That is the only justification that you need. Okay. Same as the Gallagher array thing. Okay. So let us see what happens at the check node. Okay. So if you want to do check processing, okay, you send back U, right, U1, and you are receiving V2 to VWR, right. This is what happens at the check node. Okay. So like I said, I am going to assume Vi, okay, has some distribution which is IID, and let us say I know the PDF. So let us say we call it FV, okay, IID according to some FV. Okay, maybe I can put an iteration number here, but I do not want to do that now. So let us just leave it like this. So let us see what happens when you do this. Okay. So the question is, I know U1 as a function of V2 through VWR. What is that function? It is some 2 tan hyperbolic inverse of tan hyperbolic V2 by 2 product of tan hyperbolic VWR by 2. Okay. Okay. So ultimately what I have is one function of several independent and identically distributed random variables whose distribution I know. Okay. So technically in terms of probability it is a solved problem, okay. So you must have learned this at some point in your probability course. It is a solved problem to find the PDF of u given the PDF of v, v2 to vw, okay. So it is only a question of implementation detail to figure out how efficiently I can implement that transformation, okay. So using that function f of x equals log tan hyperbolic mod x by 2 etc., you can implement it very efficiently, okay. And let me quickly show that, so because otherwise it is not very clean here. So the point I want to make is ultimately u1 is some function of some deterministic function of v2 to vwr, okay. So given fv, okay, we can find fu, which is the PDF of u using standard probability ideas. Okay, how the PDF evolves, there are several methods, okay, and you will see in this particular function, if you use the simplification I was talking about, the method will become a little bit more easy, okay. What is that simplification? You see this function if you bring the 2 down below and take tan hyperbolic on both sides, okay, you basically get tan hyperbolic of u1 by 2 equals tan hyperbolic v2 by 2 product all the way up to tan hyperbolic vwr by 2, okay. Now I want to take log on both sides, but the only problem is tan hyperbolic can be negative, okay, in which case you can't keep taking logarithm. So what people do is you separate it into 2 parts, okay. You look at the sign separately, and once you get rid of the sign you only look at absolute value and find the absolute values, okay. So you can show that this is the same as sine of u1 being equal to minus 1, should I write minus 1, let me not write minus 1, simply I will say product of the signs, okay, product of the signs of v2 all the way to vwr, okay. And in absolute value all you have to do is remember that f of absolute value of u1, okay, so I messed that up, equals f of absolute value of v2 by 2, let me just say v2 plus all the way down to f of absolute value of vwr, okay, where this f of x is basically log tan hyperbolic x by 2, okay. So of course mod x by 2, okay. So now remember v2 through vwr are IID according to some distribution, okay. If I do f of v2, okay, I can find the distribution of f of v2, that is just a single random variable transformation, the standard formula method will work, okay. This is an increasing function, you can do the standard formula method, it will work, okay. And then what do you have? You have summation of independent random variables which will become convolution of the PDFs, okay. So all you have to do is implement a convolution here, which is very efficiently implementable using fast Fourier transforms. For instance, if you want to do a finite convolution, you take an FFT, it is very easy to do that, okay. And then how do you find the PDF of u again? You have to do a f inverse, okay. It turns out f inverse is equal to f for this function, okay. Log tan hyperbolic is its own inverse, okay. So all you have to do is then have some method for doing a transformation by f, and then have some method for doing a convolution, both of which are very standard operations. Once you have those two things, you can find the PDF of u1, okay. So using these two formula, okay, fu can be found efficiently. Using FFTs and lookup tables. Okay. And you might wonder why I am worried about efficient implementation. It is quite important that you have an efficient implementation for density evolution, okay. The reason is when you are trying to optimize the degree distribution, you are going to look at thousands of degree distributions, and for every degree distribution you have to compute the threshold. Okay, computing the threshold will involve several runs of density evolution. Okay, at least let us say 10 runs of density evolution, even maybe 1000 runs of density evolution to get an accurate threshold. Why do you need so many runs? Okay, yeah, I mean, look at the definition of the threshold. How is threshold defined? It is the largest parameter for which the probability of error goes to 0. So you have to run density evolution several times till you keep finding that. Okay, so in the numerical method for finding that, that's also 1000. So you are running this density evolution step thousands of times. Okay, so several, maybe even millions of times. Okay, so you have to have a very efficient process for this, and this FFT and lookup tables give you a pretty good, pretty decent process. Okay, so I know I didn't give a very complete step by step method, but I think hopefully you see the idea here. So the idea here is, from this message that you are sending from check node to bit node is ultimately a function of a deterministic function of the incoming extrinsic messages. Once you assume the incoming extrinsic messages are IID according to some distribution, and that distribution is known to you, you can compute the distribution of U, and because of the structure of this tan hyperbolic and all that, it can even be done reasonably efficiently. Okay, that is the big idea here. Okay, now let us move to the other side. If you come to the bit processing, okay, what happens with the bit node is even easier. Okay, you have Li, and then you have one V1 going this side, and then you have U2 all the way down to UWC coming in from this side. Okay, and what is my V1? V1 is simply a summation of U2 all the way down to UWC. Okay, I know the PDF of this. This is normal, mean 2 by sigma squared, variance 4 by sigma squared. I know that all these guys are IID according to some FU. Okay, how will I find the distribution of V now? Simple convolution. Okay, so all you have to do is convolution. Okay, so FV can be found by convolution. Once again, convolution can be discretized form of it, can be easily implemented as an FFT, which is very efficient. Okay. Okay. So at least it seems theoretically clear that there is going to be a method, density evolution method. Okay, density evolution method is very easy to come up with. Okay, you have to track the density as it goes through bit processing and check node processing. Okay, so in fact, if you want, you can write notation. Okay, write everything in notation, but before that I want to move on to irregular codes as well. Okay, so far I have been talking about regular codes, but everything that we said so far can be extended to irregular codes also. Okay, same ideas extend to irregular code. Okay, what are the additional things you have to do for irregular codes in density evolution? Okay, so the problem in density evolution for irregular codes is all the neighborhoods are not identical, right? You have, so when you assume that all the messages are IID, really that assumption will immediately go wrong, okay, in irregular codes. So how did we get around that assumption? Okay, so you have to average over all the codes in the ensemble. Okay, so this extension happens if we average over all codes in ensemble. Okay, but we can do that and still get away with it, because why is it that we can get away with it, get away with the averaging? Why doesn't it affect anything else? The reason is we have a concentration around the average result. Okay, so there is also a concentration around average result. Somehow that is not happening in your quizzes. Okay, there is no concentration around the average, but in this case there is a strong concentration around the average. Okay, So even if you do analysis with the average, you compute the average and you show that the average is going to 0, okay, it means that any one code also is very likely to obey that average rule, okay. So it will also go to 0, the probability will also go to 0, okay. So very similar ideas can be extended. Once again, the tricky issue in irregular codes will be the neighborhoods are not the same, okay, depending on the degree the neighborhoods changes. So you have no business saying assuming IID for incoming messages, but if you do not assume IID, there is no way you can do density evolution, okay. So how do you get around that? You get around that by averaging over all the codes in the ensemble, which gives you the IID property, okay. But then the problem is, then you only get the average block error rate, average of all the densities. I mean, is it really the real one? How do you answer that? You answer that by showing a concentration around average proof. So you say that if you pick any one candidate code from the ensemble, it is very likely to be very close to the average, okay. So once you show all these things, all the pieces fall together and you can trust your density evolution, okay. So one final thing is, let us just put everything together now, okay. So let us put everything together and talk about density evolution for the soft message passing algorithm, okay. So we will let us say capital UL denote a random variable that denotes, denoting what? Denoting U is a check to bit message, right, denoting the check to bit message in Lth iteration. Remember, once again, this is averaged, this random variable is averaged over several things, okay. It is averaged over all the channel realizations first of all, okay, different channel realizations, and it is also averaged over all the codes in the ensemble, okay. So what do I mean by averaged over channel realizations? Well, all possible channel outputs, right. So that's how we are assuming Ri is normal with mean 1 and variance sigma square. So that's our assumption for R, right. Go back and look at the received vector R, okay. So clearly the one averaging is definitely happening over the channel realizations, channel noise realization, but the other averaging you have to do for irregular codes is also over all the codes. For regular codes you do not have to do that, but for irregular codes you have to do that also. And then VL will be corresponding for bit to check message, okay. It is a corresponding random variable for bit to check message, okay. Then what you can write is the following kind of rule, okay. So you can write, so I am interested in tracking the PDF of VL, right. So I need, okay, so I have the following rule for the check processing at the check node. The rule that I have is sign of U or V, U, right, UL equals sign of, let me write V2 or let me write V1, okay, V1L all the way down to sign of V. So let us say check node of degree j, okay, then it is Vj minus 1L, okay. What are these V1 through Vj minus L? These are all IID according to the same distribution of VL, okay. And then I have magnitude of UL equals f of V1 L plus so on till Vj minus 1 L. Okay, so this is a check node of degree j, remember check node of degree j. Okay, and I have bit nodes j minus 1 bit nodes will contribute to this message. The message going in this direction is UL, and what comes here is V1 L all the way down to Vj minus 1 L. Okay. So, this is the equation that we wrote just now for the check processing at a degree j check node. Okay. So, what is f of x? F of x is log tan hyperbolic mod x by 2. Okay. So, this is ultimately some transformation. So, what I can do is I can write the PDF of UL can be written as FUL will be can be written as some function. Okay, I will say what this function is of a convolution, this denotes convolution j minus 1 times capital F of the PDF of VL. Okay. All right. So, this FVL is the incoming PDF. Okay. Capital F denotes transformation by f of x, which is log tan hyperbolic x by 2. Okay. So, you have the incoming PDF for VL. Okay. Of course, this has to be for the absolute value of VL, I am sorry. Okay. Let me write down absolute value of VL. Okay. And then you look at the transformation by log tan hyperbolic x by 2, you will get some PDF. You convolve it j minus 1 times, you will get the new PDF. Okay. And then I have a function here, and this function has to account for the sign also. Okay. So, this has to account for sign of VL. Okay. We never took care of sign of VL in this convolution. So, you have to account for the sign of VL, that is not too difficult. Okay. So, you have to do that. If you do that, you will get some FUL. Okay. So, it is not an explicit thing, but you at least understand the method behind it. There is an algorithm that you can come up with to find the PDF of UL. Okay. Now, this is for a degree j check node. Okay. When you do irregular codes, you have to average this over a randomly chosen edge. Okay. So, when you do that, okay, so this is for regular. If you have irregular, FUL will basically be summation over j rho j, the same function that accounts for the sign. The convolution will be j minus 1 times f of f mod VL. Okay, so, this function will also involve j and all that, right. So, it will have something there. Okay. So, this complicated function can basically be denoted rho. Okay. So, this is some standard notation, usually people use this. You write this as some rho of f VL. Okay. I could have just written this directly, but anyway I thought I will write down the mechanics also. Okay. So, given the PDF of VL, okay, so in this picture, given the PDF of VL, we can find the PDF of UL, okay, and that PDF, that transformation is denoted rho. Okay. So, same thing you can do for the bit processing also. I am not going to repeat it, that is a little bit easier to write down, but at the bit nodes you can also do a very similar thing. Let me just quickly write down one common final expression here. You know that u, it is not u, it is VL plus 1 is basically going to be Li, okay, small li, sorry, plus u1 L plus u2 L so on till u I minus 1 L. Okay. So, if this degree is I. Okay. So, if you look at it, basically the PDF of V L plus 1 is basically going to be summation over I lambda I. Okay. The PDF of Li. Okay. What is the PDF of Li? This will be normal with mean 2 by sigma square and variance 4 by sigma square, convolved with, okay, a convolution I minus 1 times of simply the okay. So, this is I minus 1 times convolving the PDF of UL. Okay. So, you can maybe denote this as, okay, so you can denote this as FLI convolved with, convolution is linear, right. So, it will commute with the summation. So, you can write it as some lambda times FUL. Okay. Now, what is FUL now? FUL I know is rho of FVL. Okay. So, ultimately I have this being FLI convolution lambda rho FVL. Okay. This is the final density evolution for soft message passing. Okay. So, I think the time is up. So, we will stop here for now and we will take a small break and continue in about another 10 minutes.